So here we are going to look at another solution concept for the incomplete information game. Earlier we discussed the Bayesian Nash equilibrium. Now here we are going to consider the perfect Bayesian Nash equilibrium, or you can just call it perfect Bayesian equilibrium. So this is the same game we discussed previously to analyze the Bayesian Nash equilibrium. So here nature determines, the type of player one. Player one can be either a friend with a probability P or enemy with a probability 1 minus P. So nature reveals, the type to player one. Player one knows his type, whether he is friend or enemy, but player two does not know that. So in that sense, this is an incomplete information game. So player two so player one can give gift as a friend type or enemy type, or not give gifts as friend type or enemy type to player two. And then player two has the option of accepting or rejecting the gifts. So it's the same game we considered previously. Here, what we are doing, additionally, is that player two, upon receiving the gift, will update her belief about player two's type. So the updated belief is given by probability Q. This is player two's belief upon receiving gift, whether she's dealing with the friend or enemy type, right? So this is updated belief. We use Bayes rule to update the belief. So given player one's action, right, player two has more information about player one's type, and therefore she can update her belief, the prior belief, about player one's type. So to solve this game, we are going to consider two types of strategies, two groups of strategies, I should say. So the one group of strategies called pooling strategies. The other one is the separating, strategies. So let's first consider separating equilibrium. So we are going to separate player one's strategies for the two types and analyze them, whether they can constitute equilibrium in this game or not. So separating perfect Bayesian equilibrium. So one separating strategy for player one would be to give gift as a friend type and not give gift as enemy type, right? So you're looking at this and this strategy, right? So player one is going to announce that he is going to give gift if he's a friend type, right? And as a friend type, he's going to give gift, and as an enemy type, he's not going to give. This is the player one's announced strategy. So then player two, upon receiving the gift, knows that she is facing the friend type, because friend, that's what the announced policy is. So in that case, the probability that she's dealing with a friend is 1. So Q, her updated belief about the type of player one, is equal to 1, because she knows that only friend type gives the gift here, right? Of player one gives the gift. So in that case, she will update her belief to Q equals to 1. So now, if that's the case, then C is going to choose accept, right? So player two will choose to accept the gift, because that will result in a payoff of 1. Otherwise, if she rejects, she'll get 0, right? So if she chooses to accept the gift, then she's going to get 1, and player one also will get 1. But then at the bottom node of player one has announced that as an enemy type, she is going to not give gift. But if he knows that player one is going to accept the gift, then C has player one has an incentive to deviate from this chosen strategy, NE, and give gift as an enemy type, because that way, if player two accepts, player one will end up with 1. So 1 is better than getting a 0. Therefore, so player one has an incentive to deviate at the bottom node. So clearly, if player one has an incentive to deviate, meaning not to choose, not to give gift as an enemy type, but give gift as an enemy type, right? Then this cannot be an equilibrium. GF any and player two accepting the gift is not a separating perfect Bayesian equilibrium, because player one has an incentive to deviate from the announced strategy. Similarly, we can consider the other separating strategy for player one. So that could be player one as a friend type does not give gift, and as enemy type gives gift. So then what happens? Player two knows that C is dealing with an enemy type, because according to the announced strategy of player one, only the enemy type gives gift, right? So you're looking at this one. So we are considering now these two strategies. So enemy type gives gift. So player two knows that C is dealing with an enemy, meaning, so C will update her belief where Q equals to 0, meaning C is here now, right? Q equals to 0 means one probability of an enemy type is 1 now. So this is the updated belief. And now player two has an incentive to reject the gift. So this would be the optimal strategy, because he'll get 0 that way. Otherwise, if he accepts, he'll get -1. So now what happens? If she rejects the gift, then player one, as you can see, has no incentive to give gift as an enemy type, because he can always deviate to not give gift at the bottom node and receive 0, which is better than -1. So clearly, player two rejecting, is the optimal strategy, but then player one has an incentive to deviate. Player one deviates from the chosen strategy. So clearly, if player one has an incentive to deviate from the chosen strategy, then this cannot be a separating perfect Bayesian equilibrium. So in this game, there is no perfect Bayesian equilibrium in the separating strategies of player one. So the next, we can consider the pooling strategies. So they play the same strategies. Basically, player one plays the same strategy. So now let's consider pooling perfect Bayesian equilibrium. So one pooling strategy would be both types of player one gives gift. So we are looking at GF and GE, right? So both types of player one gives gift. So we are considering GF and GE. So now player two does not have an extra information here about the player one's type. So basically Q is same as P here. So there's no additional information because both types are giving gifts. So Q is as good as P here. So it's the same probability. So in this case, we have to find the expected payoff of player two from choosing accept, and reject, right? So player two's expected payoff from accept would be, so she's receiving gift from friend type with a probability of Q. So, and she will, if she accepts, she gets a 1. So 1 times Q plus 1 minus Q, which is the probability of receiving gift from an enemy type. And in that case, if she accepts, she gets -1. So this will result in 2Q minus 1. This is the expected payoff for player 2. And if she rejects the gift. So U2 expected payoff of player 2 from reject would be, so C is going to get 0 in both cases, right? So Q times 0 plus 1 minus Q times 0. So this is 0. So then we can write that if 2Q minus 1 is greater than 0, meaning Q is greater than 1/2, then player 2 is going to accept the gift, right? Because expected payoff from accept is greater than reject, as long as Q is greater than 1/2. So now let's consider this. So player 1 gives gift as friend and enemy type, and Q is greater than 1/2, right? So if Q is greater than 1/2, then player 1 has no incentive to deviate from the chosen strategies, because if Q is greater than 1/2, player 1 knows player 2 is going to choose to accept, and in both cases, player 1 is going to get 1, right? And if player 1 deviates by not giving gift, then player 1's payoff is 0. So clearly 1 is better than 0. So player 1 is not going to deviate, has no incentive to deviate. So this would be a perfect Bayesian equilibrium, where player one gives gift as both as friend and enemy type, and the probability of being friend, updated belief of player 2 is Q is greater than 1/2, and player 2 accepts the gift. So this would be the pooling perfect Bayesian equilibrium in the pooling strategies. Similarly, you can analyze the other pooling strategy, which is not to give gift as friend and enemy type. So in that case, so NF and NE, right, the other strategy. So in this case, we know player 2's node will not be reached, right? But still, since we are looking at the strategies, so even in the impossible case of player 2's strategy not node not reached, in the case of surprise, we still had player 2 doesn't know whether she's dealing with friend or enemy, so Q is still equal to P. So as long as, so we already calculated the expected payoff previously, right? So as long as Q is less than 1/2, right? So if Q is less than 1/2, then we know that expected payoff from choosing to accept, right, is less than choosing to reject. So in that case, player 1 has no incentive to deviate by giving gift. So player 1 will stick to not giving gift, and probability of friend type is less than 1/2, and player 2 in that case is if Q is less than 1/2, she's going to reject the gift, right? So that would be the optimal strategy for player 2. If Q is greater than 1/2, then she would accept, and then player 1 has an incentive to switch, right? So this could also be a pooling perfect Bayesian equilibrium. So both types of player 1 does not give gift, and probability of updated belief of player 2 about player 1's type is that Q is less than 1/2, and therefore the optimal strategy for player 2 is to reject, right? So in that case, this is also a perfect Bayesian equilibrium of this game.